started this last time, but it's important section, so let's look at it. Okay, so let's go to 11.3. Partial derivatives. Okay, can you see it? Just
Yes.
no, okay. So again, so we started this last time. The first two slides are very important. So here we have a function of two variables equal f of xy. Later we will generalize this to functions of three variables and a number of variables. But for the moment, we have a function of two variables. Now, if we fix one variable, then of course we have a function of one variable. So if we fix y equal b, well, we get a function z equal f of xb. That's a function of one variable. You can call it g of x, it gives a new name. And then the partial derivative is defined like this. So partial derivative at the point AB, so that's a specific point we are interested in. Well, so partial derivative with respect to x, it means that first variable will change. So we have f of a plus h, b minus f of a, b. So b is the same, it's fixed value of y, divided by h. So again, this is derivative of the function g, but we call this partial derivative of function f with respect to x. This means, well, treat y as a constant, and then you differentiate with respect to x. So of course, that's how derivative is defined. Now, here let's look at the picture. We have a surface z equal f of xy. This is this blue surface, let's say. And now let's consider the intersection of this surface with a plane y equal b. So y is constant, equal b. So that's this yellow plane. And of course, intersecting in general surface with a plane, we are getting some curve. There's this red curve is the curve of intersection. And now let's look at the point on the plane and on the surface and on the curve. Let's look at the point AB, f of AB. So of course, this is a point here, which is on the surface. This point is on the plane. This point is on the curve of intersection. And then that's a curve. So we can think about the tangent vector to this curve. And again, tangent vector to this curve. Let's look, well, of course, that's a vector in 3 dimensions. So let's think what is the second coordinate of this tangent vector. Well, you project the end to y-axis and you project the beginning to the y-axis. And those projections are the same. So this means that the second coordinate of this vector is 0. And now, the first coordinate, well, we can assume anything. If you assume 1, then the last component is this partial derivative. Again, I explained this last time drawing the picture in 2 dimensions. It's difficult to see things in 3 dimensions. So I justified this formula for the tangent vector last time drawing the picture on the whiteboard in 2 dimensions. Of course, if you fix y, you can draw a picture in the xz plane. And then, of course, the tangent vector is, if you fix 1 here, that's the derivative. You can have any constant here, and then it would be constant times df over dx. This was the picture we had in the 2 dimensions. Now, so I justified the formula for the tangent vector. Tangent vector to this curve, which is intersection of the surface and the plane, is 1, 0, and df over dx. Similarly, you can consider the intersection of this plane with of the surface with a plane x equal a, and that's the next thing. And then also we will develop the tangent. Again, those are very important formulas. We justify this formula for T1, but even if you don't understand this, you have to remember the formula. So the tangent vector to the curve, which is intersection of the surface and the plane y equal constant, has 1, 0, and df over dx. And of course, similar formula we have if you intersect. Now you have again the surface as on the previous picture, but now we have a plane x equal a, constant plane. And then this intersection is this red curve. And let's look at the point A, B, and f of AB. This point belongs to the surface, belongs to the plane, belongs to the curve. And we can compute the tangent vector to this curve. Again, the first component of this tangent vector is 0, because if you project the end of the tangent vector and beginning of the tangent vector, you are getting the same value. Projection of this and this on the plane x equal a is AA. So the first component is a minus a, 0. Second component, you can choose whatever you like. Well, if you choose 1, then the last component is df over dy, the partial derivative with respect to y. And of course, partial derivative with respect to y is defined in similar way as before. Now, first coordinate is fixed, AA. And second coordinate is changing. So we have b plus h, b divided by h. And that's a definition of partial derivative of the function f with respect to y at specific point. This point is a, b here. So again, we know from one-dimensional calculus that df over dy is the slope over the tangent line to the surface, and because of this, the tangent vector takes this form. So those are very important formulas. You will see that we will be using them all the time to get the equations of the tangent planes and so on. Again, try to understand those things, why this is tangent vector and why this is tangent vector. But again, even if you don't understand, you have to memorize the formula, and you'll be able to do a lot of computations just using the formula. Just knowing that the tangent vector to the surface in the y direction is 0, 1 dy over df over dy. Tangent vector in the x direction is 1, 0 df over dx. So those are difficult slides. Try to think about those. So if your goal would be understanding of this formula for T1 and T2. If you understand this, this would be perfect. So try to understand the formula for T1 and T2. This will make understanding what follows much easier. So again, those are not trivial slides, yeah, kind of somewhat complicated slides. And now some technical things. Partial derivatives. Well, so df over dx, that's a partial derivative of f with respect to x at the point AB. Different notation is we put f with subscript x. So that's just different notation for the same thing. So we call partial derivative df over dx or fx. And similarly, df over dy, different notation is fy. So read this, differentiate f with respect to y. So just different notation for the same thing. And again, to find partial derivative with respect to x, you regard second variable as a constant, variable y as a constant, and differentiate with respect to x. To find f of y, it's the other way around. You regard x as constant and differentiate with respect to y. So here is the example. So that's easy process, of course, yeah. So you see here, function of two variables, f of xy is cosine 3x plus 2y. Well, to differentiate with respect to x, you assume that y is constant. So of course, derivative with respect to x is minus sine 3x plus 2y, and derivative of the inner function is 3. So the derivative is minus 3 sine 3x plus 2y. Similarly, derivative with respect to y, now x is constant. So derivative with respect to y is again minus sine 3x plus 2y, and derivative of the inner function is 2. So that's why we have minus 2.
Professor?
Yes?
Just really quickly, I see it's called partial derivatives, and I'm just kind of curious. In the examples, if you're taking the derivative for respect, like for example with x, you just regard y as a constant. So is it kind of called partial derivatives because you're not actually taking the derivative or differentiating y? You're kind of almost ignoring it. I mean,
yes, yeah. So basically, you just differentiate with respect to subset of variables. So that's why with respect to part of the variables, we differentiate function with respect to x only. So part of variables. So that's why the name partial.
okay, because I remember seeing like where if we took the derivative with respect to x and you had y, you'd have to like do dy over dx and all kinds of like stuff like that. So I just noticed that you're not doing that here, and that's what I was finding out.
Yeah. Here, just kind of you keep one variable constant and you differentiate. So df over dx means keep the second variable constant, treat it as a constant. That's you kind of when you do a few examples, kind of you'll see that kind of that's not a difficult concept. That kind of you will see that that's kind of reasonably kind of simple concept. Again, so just you differentiate this with respect to x only means y is constant. Yeah, so that's of course the answer. Or the other way around, you differentiate with respect to y when x is constant. So partial means, well, to differentiate with respect to everything with x and y, kind of just this will come later. Kind of this we are just doing this piece by piece. We are differentiating functions in some sense piece by piece. Also, we had the slides last time, so kind of here we are trying to guess whether or not the derivative is positive or negative. And you remember from last semester, the derivative is positive if the function is decreasing, derivative is negative. If the function is increasing, the derivative is positive. So kind of that's what we know from the last semester. So here you have this point. And now fx means, well, you have complete derivative in this direction. So it looks like the function is decreasing. Yeah, if you move in the x direction from the point P, you are sliding down. So the function is decreasing. So this means that the derivative with respect to x is negative at this point. Now, if you try to move in the y direction, well, if you go, y goes this way. So you see the function looks like it's increasing. You go this way, and after the y, you are here, you are higher. So derivative with respect to y is positive because the function is increasing as you move from this point to the point with bigger y. So that's the kind of interpretation. But again, those two-dimensional pictures are not always easy to read. So here kind of just, okay, we are here, so you see that we are going up here and we are going down here. But in general, it may be quite difficult to figure this out. If you have quite complicated surface, you may have to zoom and so on really to figure this out. you will have a similar web problems like this, I assume. And here, we can also kind of try to estimate partial derivatives using so-called contour plots. Contour plot means the following, kind of that, let's say you intersect the surface corresponding to the function with planes z equal something, z equal constant value. So for example, this circle here, or ellipse, is intersection of the surface with the plane z equal 2, this one, z equal 1, z equal 2. No, I think here, z equal minus 2, z equal 2, and so on, kind of. So those are so-called contour plots. In MATLAB, you can kind of plot contour plots, just the name is contour. And then we would like to estimate fx, derivative is at the point 1, 0, and fy is the point 1, 0. So of course, the point 1, 0, 1, x is 1, and so it's here. This is the point 1, 0, that's a point capital A. So to estimate at this point, well, so what you can do, well, okay, if you would like to estimate fx, well, we compute value at the point B minus value at the point A, and then divided by the distance between those 2 points. So here, what is the value at the point B? Well, so those are those red things are the values. This means kind of this is the level, z equal 4, z equal minus 2, z equal 0. So this is the value of the function is 4 all over this curve, and so on. For example, on this curve, the value of function is 12. So that's the notation for those contour plots. So value of the function at B is 4. Now, what is the value of the function at A? Well, the point A is on this curve. So the value of the function at the point A is 2. Well, so we estimate f of B minus f, so 4 minus 2. And then what is the change in x? Well, so here, x is 1 here, x is 2 here. So roughly speaking, x is 1.5 here, roughly speaking. So the distance between A and B in the x direction is just 0.5, 1.5 minus 1. So of course, if you compute this, you will see that the partial derivative with respect to x is more or less 4. And of course, you see that it's positive because the function is increasing. At A, the value of function is 2. At B, the value is 4. So of course, the function is increasing, which tells us that the derivative is positive. And of course, this agrees with this. Again, that's this kind of somewhat tedious process, kind of, yeah. And of course, this is just a rough estimation of those derivatives. Now we try to estimate derivative in this direction. So of course, again, we will use the point A and we will use the point C. So again, the partial derivative with respect to y will be f of C minus f of A divided by the y coordinate of C and y coordinate of A. You see that the y coordinate of C is 1 and y coordinate of A is 0. So downstairs we have 1 minus 0. And of course, upstairs we have here the value of the function is 2 here and the same value here at the point C. So the partial derivative with respect to y is 2 minus 2, so that's 0. So kind of the function is not changing value. Yeah? Value here was 2. At the point C, still value is 2. So roughly speaking, of course, that's only approximation. Partial derivative with respect to y is 0. So again, if you have some surface and you plot the contour plot, the MATLAB will give you those values, kind of just. It will tell you that this contour corresponds to 2. This contour corresponds to 12. So the height here is 12. Height here is 9. Like, think about the map. Kind of, this is kind of valley here. Yeah, and here the height is 2. Here is the sea level. And here we are going down. Kind of, so that's the valley. And here, of course, if you go like this, you are going up. Yeah, you are going here. Height here is 9, height here is here. So going this way, we are going up. Like on the map, you read contour plots the way you read map. And kind of on the map, they would put a color here. They would put here red color and they would put a green color. Red color would correspond to mountains, and green color would correspond to valleys. So basically, contour plot is more or less a map of a surface. Same thing. Another example. So again, you have a contour plot. So again, think about this like this. That's the same contour, I think. Yeah, same. So contour is the same kind of, but now they want you to estimate those partial at the point -1 and 1. So at the point D, they want you to estimate partial at the point D. So again, you will use to estimate in this direction. You will use a point E and D. To estimate in this direction, you will use a point D and F. So to estimate Fx, well, this is F of E minus F of D, and the distance between those 2 points. The distance between those 2 points here is -1. Yeah, kind of, it's difficult to say, but kind of you see that if this is D is 1, X coordinate, E is more or less 0.6 or 0.7. They assume that that's 0.7, okay? Again, this is just estimate, rough estimate. So F of E, what is the value of on the contour E? You see, it's 0. Yeah, on the contour is it. What is the value of this contour? Well, it's 2. So 0 minus 2, F of E minus F of D is 0 minus 2. And then XE is minus 0.7 minus 1. So that's minus 0.3. So that's minus 6.67. So of course, going from here to here, you see that we are going down. We are moving from height 2 to height 0. We are moving from level 2 to level 0. We are going down, and of course the derivative is negative. Again, this is tedious process. I believe you have something like this on the web work, kind of, yeah. So you'll have to pick up kind of some of the points and do this thing. Why? Well, we are going this way. You can see here that here is the value is 2. At the point F, the value is 4. So it looks like we'll be going up. Going from D to F, we'll be going uphill. And of course, this will reflect that derivative will be positive probably. This is what we'll get in a moment. So again, F of at the point F minus F of the point D and the distance. Here is 1, so here is more or less also 1.7. So it looks like, well, they assumed 1.8, okay? So this coordinate here is, well, maybe 1.7, 1.8. Well, 1.8 is fine. So the difference in X is 0.8. And then, of course, value of the function at the point F, as you see, is 4. Value of the function at the point D is, as before, 2. So we have 4 minus 2 over 0.8. That's roughly speaking 2.5. And again, it's positive because going this way, we are going up. From D to E, we are going down. From D to F, we are going up.
Can you explain where the 0 and the 2 came from for e to d once more?
0 here.
It says f of x negative 1 to 1 is equal to f of e minus f of d, and you put, and then it says a 0 minus 2. Up one example.
It's not 0 minus 2, it's 4 minus 2.
No. If you go up one example.
This example?
No, it's down. It's on the same page, just the first one. F of e minus f of d.
This one.
Yeah.
F of e minus, no. So look, what is the value at the point E? The point E is on this curve here. I'm moving the things. What is the value? Well, 0. That 0 is here.
Oh, okay, I got you. Okay, makes sense. Thank you.
Professor, will those values be given like in each example like this one?
Of course. Well, you see, so kind of, for example, x, y is not given. So what is the y coordinate of the point F? Well, you just estimate it between 1 and 2, much bigger than 1, less than 2. 1.8 looks like it's a reasonable estimate. So kind of, if this is not given, maybe you will have to estimate. So for example, if you would need a curve between this and this, the value here is 0, the value here is 2. So what would the value on the curve in between? Well, if the curve is in the middle, maybe the value of the curve of function would be 1. But of course, it's not written here. So when you have a MATLAB command, MATLAB, then you can request that you want contour plots, let's say between 0 and 1 in increments of 100, and then you'll have a lot of lines. But of course, then when you have a lot of lines, also kind of then difficult to see anything. Yeah, so again, if the values are not given, you will have to kind of try to estimate it. Like we are estimating the y values, yeah, or x values. Okay, so this is the second example. Okay. Oh, it takes a long time. Okay, higher order partial. Of course, you can compute those derivatives as many times as you want. So here is kind of the diagram. You have a function f of xy, you put it here. When fx or d over dx, that's the same notation for different notation for the same thing. You can compute d fy or d over dy. Then you can compute, you can take derivative of this with respect to x once more. And then the notations fxx means differentiate f with respect to x twice, or notation using those deltas is delta squared over delta x squared. Here, you can also differentiate twice with respect to y. Or you can differentiate, here you differentiate with respect to x, and then you can differentiate the function again with respect to y. The notation will be f of xy. It's not clear what's here, but this is fxy, or the d squared dx dy. Here you can first differentiate with respect to y, then with respect to x. And there's a theorem in calculus that those mixed derivatives are always the same. The theorem has a name, Clairaut. So assume that the function f is defined on some open set on the plane, and that f of xy and f of yx are continuous. Then those partial derivatives are equal. So you can differentiate it first with respect to x, then with respect to y, or the other way around. The answer is always the same if the function f is smooth enough. And this holds for higher derivatives as well. So for example, f, x, y, you differentiate with respect to x, then with respect to y, and again with respect to x. Well, you can differentiate with any order. That's f of yxx or fxxy, assuming that the function is just smooth enough. So this is important theorem, Clairaut. You can compute partial derivatives in any order, and this doesn't matter.
Professor, is is f of xy or f of yx, is that still a partial derivative, or since we're doing both variables, it's not partial anymore?
No, it's still a partial derivative. Well, that's a partial derivative with respect to x and y. Yeah, but it's still partial derivative. We are computing this. When you compute f of x, y, first you keep y constant and then you keep x constant. But the name is still the same, partial derivatives. So this one is mixed partial derivatives.
Oh, okay, thank you.
The name is still the same. Those are still partial derivatives. So here is example. Function is f of xy is y tangent to x. So again, if you compute fx, means y is constant. So of course the derivative is y, and derivative of tangent is secant squared, and then derivative of the inner function is 2. So fx is 2y secant squared to x. Well, derivative with respect to y is simpler. Y is just x is constant, so the derivative with respect to y is just tangent to x. Of course, now if you compute fyy, that's 0 because this is independent of y. So fyy, partial derivative with respect to y twice, is 0. Well, f of xx, of course, it's derivative of secant is secant tangent, yeah. So we have 2 secant to x and secant tangent, so we have secant squared and tangent. Of course, those are just differentiation from the last semester. And f of xy, well, if you compute with respect to y, you get 2 secant squared to x. And of course, here, if you compute with respect to x now, that's also 2 secant squared to x. You see that they are equal. We know this from the theorem, but kind of that's a confirmation that they are equal. And of course, you can compute derivative of higher order, x, xy, and so on, kind of. You see that all of them, you do this in different order, you will always get the same answer. Just check it at home if you want. So there are no computations here, yeah, but kind of, for example, f of x, xy, to compute this with respect to y, of course, it's 8 secant squared tangent squared. To compute with respect to x, same thing, and so on. So just check that those are just differential formula we know from the last semester. And that's the last. So again, we were talking about 2 variables, but of course you can generalize everything to 3 variables and any number of variables. So here is example with 3 variables. We have a function f of which now independent arguments is x, y, and z. So this function is x, y squared z cubed plus 3yz. That's the function example. And now find f of x, f of y, f of z. So again, to find f of x, you keep y and z constant. To find f of y, you keep x and z constant. And to find f of z, you keep x and y constant. So that's the approach. So that's written here. To find fx, regard y and z as constant and differentiate with respect to x. So of course, if you differentiate this with respect to x, you will get y squared z cubed, and that's 0. Yeah. Derivative with respect to x, of course, is y squared z cubed. Derivative with respect to y, well, it will be 2xy z cubed plus 3z. Yeah, if you differentiate, so again, to differentiate with respect to y, keep x and z as a constant. So you have 2y x z cubed plus 3z. To derivative with respect to z, well, keep now x and y as a constant. Well, so x, y squared is a constant, so with z cubed we have, so 3 x, y squared, z squared, 3 x, y squared, z squared. And derivative this with respect to z is plus 3y. So again, you can do this in any number of dimensions. Yeah. So most of the time we will deal with 2 dimensions, but you see this also works for 3 dimensions and any number of variables. So again, f of x to differentiate with respect to x, keep y and z constant. To differentiate with respect to y, keep x and z constant. To differentiate with respect to z, keep x and y constant. Okay. Any questions so far?
Do you have any remarks on the test we took last week? Anything like, that you noticed that we should improve on for like any upcoming?
Not yet. I didn't put the grades yet, and so I didn't have time to. Probably I will do this today. So maybe I will discuss kind of how you did, kind of average, median, and so on. Maybe next time, so you'll be able to put yourself kind of in the class. But yeah, so probably by next time.
Sounds good.
Mm-hmm.
Is there a way you could like open up the test, I guess, just to see like what questions we got wrong?
Not yet, because there's some mix-up. So the test will be open as soon as as all the make, because kind of some people couldn't take the one person was in the hospital and so on. So there'll be still makeups. But once I finish all the makeups, the test will be open.
Okay, thank you.
But not yet. Wait a few more days.
When will our next web work be due? Because we don't have anything open for 11.1 or 11.3.
I will open this today. Well, let me, yeah, I forget to do this. 11.1 and 11.3. I will open this in 1 hour, and you'll have more or less 10 days or something.
Thank you.
There should be enough time, more or less, let's say around 10 days. So today is what, 15. So let's say kind of, I will close it on 25th or something like this.
Sounds good.
Mm-hmm.
And I'm assuming like we're skipping 11.2, right?
Correct. If it's not on the syllabus, this means they are skipping. And if there's a homework on 11.2, I will not open this, and don't worry. If there is a web work shows that there's a homework and it's not open, you are not responsible for this. I will only open those homeworks we are covering in class. Okay, so let's start next section, just maybe 1 or 2 slides. So I will again share the screen, and I will go to so tangent planes, very important section, extremely important. We will try to write equation of the tangent plane to a surface at some specific point. Now what's happened? Oh, gee. 11 point for tangent planes. Okay. Tangent planes and linear approximation. Again, I will repeat this next time as well, but kind of just here. Yeah, so maybe two slides, or maybe only one. Let's see what happens. Tangent plane. So here is a situation. You have a function, you have a surface S, which has the equation z equal f of xy. So of course, function to variables in general describe a surface. This is this blue surface. Now we are assuming that function f has continuous partial derivatives, so the function is nice. And we are fixing a point P with some coordinates x0, y0, z0 on the plane, on the surface. So that's a point on the surface. Let's pick up some specific point on this surface. So P is a point on the surface. Now, we can intersect this surface by planes. Plane y equal y0 and plane x equal x0. You remember we had this kind of on the previous slides when we discussed tangent vector. So here, this red curve is intersection of the plane C1. So let's see. Let's C1 and say be careful with the intersection of the. So C1 is y is constant. So that's this blue curve. And C2 x is constant. That's a red curve. And then, of course, we can compute tangent vectors to this blue curve and tangent vector to the red curve. This is the first slides in previous section. You remember I mentioned that the tangent vector in the direction of the direction of the tangent line to the curve C1, when you intersect this surface with the plane y equal y0, means that the second component is a 0. So the tangent vector, that's what we had on the previous slides. It's 1, 0, and partial derivative with respect to x. At this point, we are interested in x0, y0. And now the direction of the tangent line to the curve C2. C2 is intersection of the surface with the plane x equal x0, is T2. So now, because x is fixed, the first component is 0. Yeah, again, you take a vector and you project it into x equal x0. Of course, the first coordinate is x0, beginning is x0, and end is x0. So x0 minus x0 is 0. And then 1 fy. So those are those tangent vectors. So now, if you would like to write equation of the tangent plane, this pink one here, well, to write equation of the tangent plane, you need a normal vector. And of course, you see that you can get a normal vector if you compute the cross product of T1 and T2. Cross product of T1 or T2, it points like this. That's a perpendicular to the tangent plane. And now, so we have a normal vector. Normal vector will be T1 times T2. The point is x0, y0, z0. So of course, the equation of the plane is normal vector dot product r minus r0. So here it is. So again, normal vector is T1 times T2. If you compute the cross product of this, computation are not given here, but you see that it's easy to verify that the normal vector is minus fx, minus fy, and 1. And the plane is coordinate n1, x minus x0, plus n2, y minus y0, plus n3, z minus z0. Of course, first coordinate of the normal vector is minus fx. So minus fx, x minus x0, minus fy, y minus y0, and 1, z minus z0 equals 0. So that's a tangent plane. If you solve this for z, you will see that z is equal to z0 plus fx, x minus x0 plus fy, y minus x0. So that's equation of the tangent plane. Again, very important slide. Try to understand this. T1 and T2, those tangent vectors were developed on the first slide from in section 11.3. So the formulas for T1 and T2, those are said that those are important slides. The first two slides, on the first slide on the previous section, we had T1. On the second slides in the previous slide, we had T2. So those are the formulas we are using now for those vectors. And we have equation of the tangent plane. So that's how the tangent plane, equation of the tangent plane to the surface at specific point looks like. Now, so let's stop here. I will go through this slide again, but try to read it in advance. And again, try to understand this. In 3 dimensions, kind of sometimes it's not so trivial to see things. You remember we developed those vectors drawing the picture in 2 dimensions. So we justify this using the picture in 2 dimensions. In 3 dimensions, it's difficult to draw things. But this picture here is quite nice. So that's all. We go through this example next time and so on. So again, I will start from the beginning next time. So we will discuss this again, but try to understand these slides. That's the probably most substantial slide in section 11.4. So thank you.
Thank you, Professor.